So now the fact that I have given you this equation, I'm going to call this equation A. So we are in Newtonian mechanics. We cannot just accept that that is an equation that we need. We have to develop it from all the methodologies that we have learned. Okay, so we have basically learned in the last 4 chapters, 2, 3, 4, 5. How many methodologies? What did we learn in chapter 2? Conservation of energy. What did we learn in chapter 3? Newtonian mechanics. What did we learn in chapter 4? Lagrangian mechanics. What did we learn in chapter 5? So we should be able to develop that equation A from every single methodology that we have developed. Agreed? So remember this equation, A? Keep it in our minds. That's what we're looking for every single time. So let's start with chapter 2. Any objections to starting from chapter 2? What did we learn in chapter 2? Energy consideration. What was mechanical energy? Anyone remember? Total mechanical energy. Kinetic plus potential. Total kinetic energy, total potential energy. So we have a mass attached to a spring. What's its potential energy here? And when we extend it outwards by, say, delta x, which I'm just going to call x, but know that it is delta x. Imagine if I put this equals to 0, this is just x moving back and forth. What will it be at maximum x? So at maximum x, what will be its potential energy? And what will be its kinetic energy?
Potential energy is 0.
Good. Why?
Because it's at the extent of...
Because it has to stop before it returns.
Yes.
Good. What will its potential energy be at that point? Anyone remember the potential energy formula for a mass on a spring? 1/2 kx squared. Where k is the spring constant, x is the extension away from the origin. Okay, now what about at the middle? What will its potential energy be right here? Actually, let me change the color. Pick a color. Green. Potential energy at the center. Technically 0, right? Because it was resting there. So what will be kinetic energy at this point? Can I plug all of these values in here? Since I'm talking about the total kinetic energy and total potential energy, can I just write this as and what is the total energy? A constant. Between all of this, it will remain constant. The amount that it loses the kinetic energy is the same amount that it gains potential. Can it have more potential at some points and less potential at others? Yes, but the total energy will remain constant. Can I differentiate? Will this become, what's the differential of a constant? Can I write this as 1/2 m? Now I'm differentiating with respect to x dot. Will that be 2x dot x double dot? Because it's like this. Is that not equals to 2x dx over dt? Can I not write this as 2x x dot? So then if I differentiate d over dt of x dot squared, will that not be 2x dot dx dot over dt? Which is 2x dot x double dot. Yes? Okay. I'm going to still erase this. So far so good? Plus 1/2 k 2x x dot. So far, so good? Now, will this result in those two go away? Am I left with mx dot x double dot plus kxx dot equals 0? Is x dot equals to 0? No, right? That's the velocity. It can't be 0. Unless we're talking about extremums, which we're not. We're talking about all of it. So this means 0 equals x double dot m plus kx. Which means this implies md squared x over dt squared plus kx is my equation. Woohoo!